Hello again. In the last video, we introduced the four types of filters and we analyzed deeply the RL low pass circuit. What did we find? We found the type of the filter of a simple series RL circuit, which was like this. We had an inductor on the top and a resistance at the bottom where V output is measured on the resistance. Okay, so we found the type of the filter, find the transfer function, the magnitude of the transfer function, the phase angle of the transfer function. We also found maximum magnitude, and I showed you how do we extract the cutoff frequency. Okay, let's continue on analyzing this low pass RL circuit, but with a different question. Now, a low pass RL circuit where L is 100 millihenry and cutoff frequency is 10 hertz. Find R. Okay, let's begin. Find R. Now, our circuit, you should know the circuit of a low pass RL circuit. We have an inductor in the numerator and a not the numerator on the top, and the resistance at the bottom. It's as follows. Okay, so what is R? We know that already that omega C is equal to R over L. Now omega C here it's the cutoff frequency, but it's given in hertz. You need to take care of this. Whenever you have a frequency in hertz, then you have to convert it to the angular frequency, which is omega equal to 2 pi f. So omega C, this is Fc, that's Fc. Now omega C is 2 pi 10 hertz, which is equal to 20 pi rad per second. Pardon me, 20 pi is equal to R, which is unknown, over 100 milli. This will give us 6.28 ohm. Okay, so that's how we find R. Just make sure that whenever they ask us for R or L or C, you always use already existing equations. For example, omega C, beta, as we are going to see later in the band pass, omega naught, Q, quality factor. We'll discuss this later. So whenever the question asks for a constant number like find R, L, or C, you just use those ready equations. Okay, let's move on to part B. What is part B? It says find the output voltage at frequencies 1 hertz, 10 hertz, and 60 hertz. A sinusoidal input voltage of 1 volt peak is applied. Okay, so they need the output voltage. How can we calculate the output voltage? Now, so far, what equations do we have that has an V output? One of the equations that we already know is the H of S, which is transfer function. Okay. Now here, this is V output, but are they looking for this specific V output? No. Why? Because this V output is in terms of S, hence it's an imaginary number. Okay, even the V input, see, it's in terms of S, which is an imaginary number, whereas in the question here, V input is 1 volt peak, that's a real number. Okay, so another equation that has V output is the magnitude, actually, the magnitude, okay, which is equal to V output divided by V input. So the magnitude has V output as a real number and V input as a real number. Okay, so if we are looking for the V output, it's equal to the magnitude multiplied by V input. Now V input is fixed, it's 1 volt, right? 1 volt peak. And the magnitude, actually, it depends on what? It depends on omega. Depends on omega. Now omega is the angular frequency, and in the question they gave us 3 angular frequencies, actually 3 frequencies which you need to convert to angular frequencies. Anyhow, so let's begin. Now, in order to find the magnitude, you need to find its parent, which is the transfer function. In the previous video, we found the transfer function. So I will just copy it down. It was R over L. You can refer to the previous video to see how we figured this out. R over L plus S. And also we found the magnitude actually in the previous video, and it was R over L divided by the square root of R over L squared plus omega squared. Okay, so now we need to find the output for 3 different frequencies. The first frequency is at f equal to 1 hertz. Now if f is 1 hertz, then omega is 2 pi multiplied by 1, which is 2 pi rad per second. Okay, let's find the magnitude first. The magnitude at 2 pi is equal to R, which was 6.28. We found it here. Okay, divided by the inductor. What is the inductor? It was 100 milli. It was given in the question. Divided by square root of R, which is 6.28 again, over 100 milli squared plus 2 pi squared. Okay, if you calculate this, it will give you 0.995. 0.995. What is the unit of the magnitude? It has no unit. Okay, it's unitless. Okay, so now we found the magnitude. We need to find V output for this frequency. So V output is equal to the magnitude at 2 pi multiplied by V input. The magnitude is 0.995 multiplied by 1. So the answer is 0.995 volt. This is the V output for this specified frequency. Moving on to the second frequency, which is at f equal to I think 10, yes, 10 hertz. 10 hertz. Omega is 2 pi f 2 pi 10, which is equal to 20 pi rad per second. Okay, again the magnitude will be 20 pi equal to 6.28 divided by 100 milli divided by the square root of 6.28 over 100 milli squared plus 20 pi squared. Okay, if you plug this into the calculator, you will get 0.707. Okay, the output is equal to the magnitude multiplied by V input, which is equal to 0.707 multiplied by 1, which is equal to 7.07 volt. Okay, now note that 10 hertz is the actual center frequency, right? This is the omega C center frequency. The cutoff frequency. Cutoff frequency. Okay, it's here defined in the question. The cutoff frequency is 10 hertz. And we know that the magnitude at the cutoff frequency is always equal to, this is the magnitude plot. Okay, we already know that at the cutoff frequency omega, the magnitude at omega C is always equal to H max over root 2, right? We know that H max is 1. Okay, so if you figure out, or if you calculate this over root 2, which is equal to 1 over root 2, you're going to get what? 0.707. So if you have noticed that this is the frequency at the center frequency, then you can just write 1 over root 2. Okay, also note that this is actually what? It's the omega c, right? So you can, instead of writing 6.28 over 100 milli, you can just write 2 pi 10 hertz, right? So you get the omega c. Omega c is equal to 2 pi fc. Fc is 10. Okay, and you can do here the same thing. The same thing goes here and here. This will make the calculation simpler. Okay, now doing the last frequency, which is f60, I guess, at f equal to 60 hertz. Okay, omega will become 2 pi f 2 pi 60, giving us 120 pi rad per second. Okay, now substituting in the magnitude, you will get, so the magnitude evaluated at 120 pi is equal to 6.28 divided by 100 milli divided by 6.28 divided by 100 milli squared plus 120 pi squared with the square root. Okay, this will give us 0.164. Okay, finding the output will give us the magnitude evaluated at 120 pi multiplied by V input will equal to 0.164 multiplied by 100, giving us 0.164 volt. Okay. Okay, so we have finished part B of the question, which is finding the output at frequencies 110 and 60. Let's go to part C. Part C says sketch the magnitude function versus the frequency. Now, what is meant here by frequency? Frequency here is meant by omega. It's not f, because whenever they want you to sketch with respect to f, then they will specify the unit in hertz. Okay, so here they need the magnitude versus the angular frequency. Let's plot it. Part C. Choose blue. Part C. They need the magnitude with respect to the angular frequency. This is our magnitude. Okay. How many angular frequencies do we have? We have 3 angular frequencies. We have the 2 pi, 20 pi, and 120 pi. Okay. We have the 2 pi, 20 pi, and 120 pi. Okay. What is the magnitude at the 2 pi? The magnitude was 0.995. It's not this number, it's actually this number. The reason is this is V output. Now, by coincidence, they were the same numbers because VI was 1. But whenever you want to plot the magnitude, you have to pick this number. Okay? So at 0.995. Can we round it up to 1? No, we can't. Because 1 is the maximum and 1 has to occur at omega 0. Okay? But now we are at omega equal to 2 pi, so it has to be 0.995. Now, of course, there's a big difference here, but it's just a sketch. Okay? 2 pi. Okay. Let's put it here, actually. This is 0.995. Okay. This is the 0.995. 0.995. For 20 pi, it was 0.707. 0.707. And for the last one, it was 0.164. Okay, so the graph will be like this. That's a bad graph. What is this? This is one of the worst sketching I have done. It has to be like this. Okay, that's better. So here it has to actually cross this one. So this is 0.995, okay? Anyhow, you get the point. Okay, so that's the magnitude versus frequency. Let's move on to part D. In part D, the question says, sketch the magnitude function in dB versus frequency in hertz. Now they're looking for the F. Okay, so let's see how do we do this. They are looking for the magnitude in dB versus F in hertz, right? F in hertz, yes. F in hertz. So here they're looking for the magnitude, but in dB, okay? And with respect to F. Okay, how many F's do we have? How many frequencies do we have? We have 3 frequencies. The first one was 1, then 10, then 60, okay? Let's write here hertz. Okay, when F was 1, what was the magnitude in dB? How do we calculate the magnitude in dB? Now the magnitude is what? The voltage gain, right? It was what? V output over V input. Okay, how do we find the voltage gain in decibels? It was 20 log the actual voltage gain. So we'll do the same thing. At F equal to 1 hertz, the magnitude was 0.995. Okay, doing the 20 log 0.995, it has to be the absolute value also, will give us minus 0.04 dB. Okay, doing the same for the other frequencies. 10 hertz, the magnitude 20 pi is equal to 0.707, okay, and in dB it will be 20 log 0.707 equal to minus 3.01 dB. Okay, at F equal to 60 hertz, the magnitude is equal to 0.164, and in dB it will be minus 15.7 dB. Okay, so those are the 3 values in decibels. Let's plot them. When F was 1 hertz, the dB is actually, not that all of the numbers are in the negative. So should they be here, the positive side or the negative side? Now they're supposed to be in the negative side, right? But as I said in the previous video, if you remember, that plotting anything on the negative side will give you the phase angle plot rather than the magnitude. So we are forced to use the positive side. How are we going to plot the negative numbers on the positive side? The solution is simple. Just pull up the 0 axis. Okay, now all the negatives will be in this area. Let's see, at F equal to 1, the magnitude in dB will be minus 0.04. Can we round it up to 0? No, we can't, because the maximum magnitude is, we know that the maximum is 1, and if you calculate the dB of H max, you will find it's equal to 0. Okay, so the maximum actually is 0 at frequency 0, but at 1 it has to be what? Minus 0.04. Okay, at F equal to 10, which is the center frequency, the magnitude in dB is minus 3.01. Okay, and at f equal to 60 in dB it's minus 15.7. Okay, now the sketch will be as follows, which is almost which mimics the behavior of a low pass filter, right? Now at the center frequency the magnitude in dB will always equal to minus 3.01. You can keep this in mind. Okay, I hope this is clear. Next part of the question, draw part E. Draw the output voltage waveform. So waveform, that means VO with respect to time, for the following frequencies, 1 and 10 and 60. Let's see. Let's do it in here. Part F, or is it part E? It's part E. Okay, so we need V output. We need to plot the V output at F equal to 1 Hertz. At 1 Hertz, what was V output? V output was 0.1, it was 0.995 volt. Okay, so we need to plot this. The waveform will be V output with respect to time. Okay, as this is only a sketch, so we will try our best to make it as accurate as possible. 0.995 and minus 0.995, that's the number in here. Okay, the next frequency is Hertz, and the output is equal to 0.707 volt. Okay, now the waveform here will be as follows, having an amplitude of 0.707 and minus 0.707. The last frequency is at f equal to 60 Hertz. The output is equal to 0.164 volt, and here it will be, let me draw it in red, 0.164. Okay, now there's something else other than the amplitude changing. What does, see here, f was 1, then it became 10, and then it became 60. What is frequency? Frequency is the number of cycles per unit time, right? Okay, so here it says f equal to 1 Hertz, which means that the time period is 1 over f, 1 over 1, so it's 1 second. So every cycle should be in 1 second. Okay, this is the second. But as it is a sketch, they will not focus on this, or most of the instructors, they will not focus on this matter. Here f is equal to 10, meaning that the time period is 1 over 10, so it's 0. seconds. So every cycle is 0.1, 0.2. So there will be 10 cycles in 1 second, and here there has to be 60 cycles actually in 1 second. Okay, let's move on. That's part E of the question. Part F says find the maximum average power delivered to the load. Pmax, maximum average power. What is the maximum average power? Now maximum average power has an equation, and it's part F, yes. The maximum average power is Pmax equal to half the load maximum divided by resistance. This is squared. Okay, so it's the same as the power, but with a half. Okay, how can we find the maximum V output? Now the maximum, actually, how do we find V output? We said V output is equal to the magnitude multiplied by V input. We said V input was fixed at 1. Okay, we need the maximum V output, so we need the maximum magnitude. The maximum magnitude, so V output max, V output is the same as V load. It's H max multiplied by 1, and H max is already 1, so V output is 1 volt. That's the maximum. So the answer will be half 1 squared over 1K. Okay. No, sorry, the R is not 1K, it was 6.28 according to the question. Now note here that you're finding the power output, right? And we said in chapter 1 that in order to find P output or P input, then we need to find the RMS. Don't forget the RMS. So here we should write 1 divided by root 2 to find the RMS value. Okay, this will give us 0.04 watts. That's part F. The last part of the question says find the average power. Find the average power delivered to the load at the cutoff frequency. Okay, cutoff frequency. What is the power at the average power at the cutoff frequency? It's P J omega C equal to P max divided by 2. This is the equation. P max divided by 2. We already found out what was P max, which was 0.04 divided by 2. This will give us 0.02 watt. Okay, so this is the answer. Now we're done for this question. Let's move on to another question. Let's see here. Copy and paste. Okay, so the question says for the series RC circuit shown in figure 14.7. The figure is, we have a voltage source VI, resistance R, and a capacitor. Okay, this is capacitor VI. Okay, so this is also a low pass circuit. Part A of the question says find the transfer function between the source voltage and the output voltage. So they need the transfer function. The transfer function is H of S. H of S is V output in terms of S divided by V input in terms of S. We start with the numerator, which is V output, and we do a voltage division. That's the relationship between V output and V input. So it will be V input in terms of S multiplied by 1 over SC divided by 1 over SC plus R, because we said that we need to convert the time domain to frequency domain, right? Okay. So H of S is equal to V output divided by V input, which is equal to 1 over SC divided by 1 over SC plus R. Okay, we are not done yet. Why? Because we need to make it in the same form as the general equation. What is the general equation in the low pass filter? It's omega C divided by S plus omega C, and don't forget the K, which is 1 for now, because we're dealing with passive filters. Okay, so we said earlier that we need to focus on the S's in the numerator. Do we have an S? There's no S. Do we have an S here? Yes, there is an S. So we need to get rid of this S. How do we get rid of this S? We multiply by S, and we do the same thing in the denominator. This will result in 1 over C divided by 1 over C plus RS. Okay, now we're done with the numerator. Let's take a look at the denominator. Is there an S? Yes. What is the coefficient of the S? It's 1. What is the coefficient of the S in here? It's R, so we need to get rid of R. So we need to multiply by 1 over R in the numerator and denominator. Okay, this will result in 1 over RC divided by 1 over RC plus S. This is the final transfer function for the low pass RC circuit. Okay, now how do you know that our answer is correct? Notice here that this is what? This is the omega C for the RC circuit, right? In the table, if you remember, in the previous video. Okay, so we're done with part A of the question. What is part B? Part B says determine an equation for the cutoff frequency in the series RC circuit. Now, in order to find the cutoff frequency, we need an equation. Okay, who's the parent of the cutoff frequency? It was the magnitude. So in order to find the cutoff frequency, we need first to find the magnitude. Magnitude is found from the transfer function. Okay, so first we need to remove the S and replace it with the JW plus JW. This is part B of the question. Okay, then we will break this into two numbers, N1 and N2. N1 is 1 over RC, while N2 is 1 over RC plus JW. Okay, 1 over RC is the A part, the real part, and B is 0. Here this is also A and this is B. Okay, finding C1 and C2. C1 is equal to the square root of A1 squared plus B1 squared, which is equal to 1 over RC squared plus 0 squared, which is equal to 1 over RC. Okay, moving on to C2, it's square root of A2 squared plus B2 squared, which is equal to 1 over RC squared plus omega squared. Okay, this is C1 and C2. The magnitude is C1 divided by C2, which is equal to 1 over RC divided by square root of 1 over RC squared plus omega squared. Okay, that's the magnitude. Now we need to find the cutoff frequency. Now I told you that if you want to find the cutoff frequency or Hmax, I advise you to draw the magnitude plot. Okay, now this is a low pass filter, so it looks like this. That's omega C, and the y-axis or the magnitude is Hmax over root 2. So in order to find the x value, we need to substitute in the y. Okay, so here we're going to say that the magnitude evaluated at omega C is equal to Hmax divided by root 2, which is equal to 1 over RC divided by 1 over RC squared plus omega C squared. Okay, Hmax is 1. Okay, and then we do cross multiplication, exactly the same steps. Okay, so this will give us square root of 1 over RC squared plus omega C squared, which is equal to square root of 2 multiplied by 1 over RC. Squaring both sides will result in the following: 1 over RC squared plus omega C squared is equal to 1 over RC squared. Okay, making omega C the subject of the formula will result in squared minus 1 over RC squared, which is equal to 1 over RC squared. Okay, now we take the square root, and this will result in 1 over RC. Okay, this is the final answer. And we know that this is a correct solution because when we found the transfer function, omega c was 1 over RC. Okay, this is the second part of the question. The third part of the question says choose values of R and C. So see here, they are looking for numbers that will yield a low pass filter with a cutoff frequency of 3 kilohertz, not the hertz. You need to convert it to omega. Now, as they're looking for numbers, then we have to use equations that are already existing. So let's use the omega c. We know that omega c is equal to 1 over RC. Okay, 1 over RC. They are looking for R and C, and they give us the center frequency. FC was equal to 3 kilohertz. So omega c will be 2 pi FC, which is equal to 2 pi 3k, resulting in 6 kilo pi rad per second. Okay, so here you will be having 6 kilo pi 1 over RC. Okay, now is C also an unknown? Choose values for R and C that will yield a low pass filter with a cutoff frequency of 3 kilohertz. Okay, so here you just need to find two values that will result in a cutoff frequency of 6 kilohertz. If we choose a resistance of 53, if we say R is equal to 53 ohm, okay, then C is equal to 1 over 6 kilo pi multiplied by 53, which is equal to 1 microfarad. Okay, this is a design question, so you need to assume one value to find the other, or you can say C is equal to 1 microfarad, which will give you a resistance of 53 ohm. Okay, good. Let's move on to the next question. Okay, the question says a series RC low pass filter requires a cutoff frequency of 8 kilohertz. Okay, use R and compute the value of C. The only equation that has all these given numbers in one equation is omega c, which is 1 over RC. Okay, omega c is 2 pi 8 kilo 1 over 10k multiplied by C. C is equal to 1.99 nanofarad. Okay, 1.99 nanofarad. Simple. Okay, so now we're done. Okay, there's one more question. Let's solve it. Here, copy. It says a series RL low pass filter, a series RL low pass filter okay, with a cutoff frequency of 2 kilohertz is needed. Using R equal to 5 kilo ohm, compute L magnitude at this specific frequency and the phase angle at this specific frequency. Okay, let's start. A. We know that omega c is equal to R over L, and omega c, they are looking for L, right? So it's R over omega c. R is equal to 5 kilo and omega c is 2 pi 2 kilo, which is equal to 0.4 Henry. That's part A. Part B, it says find the magnitude at 50 kilohertz, sorry. Now, in order to find the magnitude, you need the transfer function. And the transfer function we already computed earlier, and it was the transfer function. It was R over L divided by R over L plus JW. Okay. Now they're looking for the magnitude at 50 kilo ohm. The magnitude was also computed earlier, and it was R over L divided by the square root of R over L squared plus omega squared. Now the only thing that you have to do is to substitute in the value 50 kilohertz, 50 kilohertz. So omega is 2 pi 50 kilo, which is equal to 100 kilo pi rad per second. Okay, so the magnitude at this value will be R is 5 kilo divided by 0.4 divided by the square root of 5 kilo divided by 0.4 squared plus 100 kilo pi squared. Okay, this will give us 0.04 and it's unitless. Moving on to the phase angle. They need the phase angle evaluated at the same frequency. Now the phase angle was also computed earlier, and it was tan inverse of omega divided by R over L. Okay, substituting in frequency 100 kilo pi divided by 5 kilo divided by 0.4 will give us a minus 87.7 degrees. Okay, that's one way of solving the magnitude and the phase angle at a specific frequency. There's another way, there's an easier way actually, using the calculator. Let me show you how to do it using the calculator. Okay, the first thing that you need to do is to go to the complex mode, which is mod plus 2. It depends on which calculator are you using. I use the standard scientific calculator. Then plug in the equation, the transfer function, which was h of s, or it has to be h of jw actually. Okay, R over L divided by R over L plus omega plus j omega. So what actually you need to write is 5k divided by 0.4 divided by 5k divided by 0.4 and j multiplied by 100 kilo pi. Now in the calculator j is I. The calculator, let me change the calculator, j is I, and you can find it using the E and G button. E and G button. Okay, let's move on. Then after you plug in the equation, you have to press equal, then press on shift with 2 and then 3. Okay, now this will give you the result. And result in which form? In the form of, it will be a number, then this symbol with another number. Now the first number will be the magnitude, and the second number will be the phase angle. Okay, so, and this is a symbol. So what you will see actually in the calculator, if you solve this question, you will see 0.04, this sign, okay, and minus 87.7. Okay, of course there are more values, but I just rounded it up. Okay, We're done for this question. Now we're done with the low pass filter. Now we can do the high pass filter. High pass filter. High pass filter. Now we will repeat almost everything but on the high pass filter. Okay, let's see this circuit. Let's analyze it. Now we know that this is a high pass filter, but let's assume that we don't know and we need to prove it. Find the type of filter. Okay, find the type of the filter. So what should we do? As we did earlier, we have to substitute in two values, omega equal to 0 and omega equal to infinity. At omega equal to 0 and omega equal to infinity. Now at omega equal to 0, we have only capacitor, right? Which has an omega. So we will say capacitor is equal to 1 over SC, which is equal to 1 over JWC, which is equal to 1 over 0 infinity. Okay, here capacitor is equal to 1 over SC, 1 over JWC, which is 1 over infinity equal to 0. Infinity is what? It's an open circuit, and 0 is a short circuit. Let's redraw the circuit. We have a voltage source. The capacitor became open circuit, and this is our resistance. Okay, same thing in here, but here we have a short circuit and a resistance. Okay, what is V output in here? V output is equal to VI, and V output, no, here it's VI, and here it's what? 0. Okay, now dividing by V input so we can get the magnitude. This will result in 1, and this will result in 0. Okay, let's plot the magnitude omega with the magnitude, okay, which is equal to V output over V input. Now at omega equal to 0, what was the magnitude? It was 0, right? So here at 0 you will get a 0. Okay, and at omega equal to infinity the magnitude is 1. So at infinity the magnitude is maximum 1. So the only combination this gives us is a high pass filter. Okay, so the answer is high pass filter. Moving on, part B of the question says find the transfer function. Okay, transfer function is h of s. For the same circuit VI, we had the capacitor and the resistance. Okay, how do we start? We start by saying h of s is equal to V output in terms of s divided by V input in terms of s, and we start with the numerator, which is equal to VI, and then we do the voltage division, SC. Now h of s is equal to V output divided by V input, which is equal to R over R plus 1 over SC. We are not done yet. Why? Because we need to make it in the same form as the general equation. What is the general equation of a high pass filter? It's K S divided by S plus omega C. Okay, so let's focus on the S's. In the numerator, do we have an S? Yes, we do have an S, but here we do not have an S, so we need to multiply by S to introduce an S. This will give us RS divided by RS plus 1 over C. Now, what is the coefficient of s in the numerator and the denominator? Here it's k, but k we said it's 1, and here it's what? It's already 1, right? So we need to get rid of r. Multiply by 1 over r, multiply by 1 over r. This will result in s divided by s plus 1 over rc. This is the final answer, because, and it's correct actually, because here we have an s in the numerator, denominator s, and this is the k 1, and all of this is what? It's omega c. Okay, so far so good. Let's now find the magnitude. Magnitude is found from its parent, which is the transfer function. It has to be in the form of jw, so it will be jw over jw plus 1 over rc. The numerator is n1 and denominator is n2. n1 is jw, n2 is equal to jw plus 1 over rc. Okay, this is b1 and a is 0 actually. This is again b2, this is a2. Okay, now we need to find c1 and c2. c1 is the square root of a1 squared plus b1 squared, square root of 0 squared plus omega squared. This will give us omega. For c2 it will be square root of a2 squared plus b2 squared, resulting in 1 over rc squared plus omega squared. Okay, so those are the answers for c1 and c2. The magnitude will be c1 divided by c2, which is equal to omega divided by the square root of 1 over rc squared plus omega squared. Okay, that's the magnitude. Let's now find the phase angle. C. Actually, it has to be part D, right? Yes, part D. Part D, the phase angle, okay, which is theta. Now theta is found from the transfer function again, which is h of jw, and it was omega, j omega plus 1 over rc. We need to break this into two numbers, n1 and n2, as we did with the magnitude. n1 is equal to jw, n2 is equal to jw plus 1 over rc. Okay, omega is the imaginary number or imaginary part, and this is the real part, which is 0, imaginary, and this is the real part. Okay, now what is theta 1 and theta 2? Theta 1 is tan inverse of b1 over a1, which is equal to tan inverse omega over 0, which is equal to tan inverse of infinity. Tan inverse of infinity is equal to 1. For theta 2, it's tan inverse b2 over a2, which is equal to tan inverse of omega over 1 over rc. Okay, what is the total theta? So theta, the entire theta will be theta 1 minus theta 2, which is equal to tan inverse of infinity is not 1 actually, it is 90. It's 90 degrees. Okay, so it will be 90 minus tan inverse of omega over 1 over rc. Okay, so as we do not have numbers, you can leave it as an expression. Okay, so we're done with the phase angle. Let's move on and find the maximum magnitude. H max. Okay, do you remember what was my recommendation to you? Whenever you reach to H max and omega c, plot the magnitude. And this is a high pass filter, so it will look like this. Now, in order to find H max is the what? It's the y. Okay, so we need to substitute in the x value. What is the x? It's infinity. And the parent of the H max is the magnitude, so we will need the magnitude first, which is equal to, what was the magnitude? The magnitude was here, omega over square root of 1 over RC squared plus omega squared. Okay, omega divided by the square root of 1 over RC squared plus omega squared. Okay, now as we need the maximum H max, it's the expression evaluated at which omega? At infinity. So here we need to remove every omega and replace it with an infinity. Infinity squared is infinity, and infinity plus anything is infinity, and square root of infinity is still infinity, and infinity divided by infinity is 1 as they cancel each other out. So the maximum magnitude is 1. Okay, now moving on to the last part before we conclude this video. Okay, we need to find the cutoff frequency. Omega c. Okay, so let's draw the magnitude plot to make our life easier. Okay, this is a high pass filter. We are looking for the x value, we are looking for omega c, so we need to substitute in the y value, which is H max divided by root 2, and H max is 1. Now, in order to solve for the cutoff frequency, we need the magnitude again, which is equal to omega divided by square root of 1 over RC squared plus omega squared. Okay, we are looking for the omega c, so it will be H max divided by the root 2 omega c. We are replacing each omega with the specific omega c. Okay, now H max is 1, and then what do? We cross multiply, so this will give us 1 over RC squared plus omega c squared equal to root 2 multiplied by omega c. Okay, square root squaring both sides will result in one. No, actually, what do we need to do? Here we forgot, I think, the square root, right? Here we forgot the square root, that's why I got confused. Squaring both sides will result in 1 over RC squared plus omega c squared equal to 2 omega c squared. Okay, now placing the omega c's on one side and the rest of the equation on the other side, the rest of the expression on the other side, will result in the following. Now 2 minus 1 is a single omega c squared. Taking the square root will result in the final answer, which is omega c 1 over RC. And this answer is correct. Why is it correct? Actually, first of all, it's an RC circuit, and if it's an RC circuit, then the omega c is 1 over RC, and when we found the transfer function, okay, omega c was 1 over RC. Okay, I hope you understood everything. In the next video, we will do the bandpass filter. Thank you for listening. See you